Good morning. I am Matthew Euler, and today we are going to cover the essentials of meteorology, an invitation to the atmosphere. This topic today is going to be air masses, fronts, and middle latitude cyclones. Now, the current edition I'm showing you here is the eighth edition, but this is applicable to both whether you have the seventh edition or the eighth edition of the Essentials of Meteorology textbook. It's in chapter 8 in both textbooks, both versions, 7th edition and 8th edition. So please refer to chapter 8 in your textbooks respectively. All right, so we're going to start things off by talking about air masses. All right, and air masses are an extremely large body of air whose temperature and humidity are similar horizontally as far as straight across in the horizontal distance, as well as vertically, the vertical distance. One important term I would like you to be familiar with is what's called a source region, and this is an area where an air mass forms or originates. And the source region for an air mass is generally a flat area with uniform composition with light surface winds. So we don't want a mountainous area for a air mass source region. We want something that's fairly flat. We want flatter earth, and we want that area to have a uniform composition. Okay, and we also want lighter surface winds, because if we get too much mixing of the air, then that's just going to, it's not really going to allow an air mass to sit there, stagnate, and form. All right, moving on to the next slide. I'm just showing you in this particular image, I'm showing you temperatures, which is the upper left-hand number next to these station plots. These little circles that you see, those are known as station plots. Okay, and the upper left-hand value is an actual air temperature in degrees Fahrenheit. This is an example of an extremely cold air mass during the wintertime that has come from Canada. The source region, this looks like it's more of a continental Arctic air mass, or if I abbreviated continental Arctic air mass, CA air mass, that has come down from Canada during the wintertime. Look at the values in some of the cities here on the map. Pittsburgh, Pennsylvania, for example, has a temperature of -2 degrees Fahrenheit. Chicago, Illinois, 1 degree above 0 Fahrenheit. Minneapolis, Minnesota, -15 degrees Fahrenheit. And if you look even further south in association with that Arctic high pressure system, the blue H there over Mississippi, you'll see temperatures as low as 9 degrees above 0 in Georgia, 28 degrees Fahrenheit there in North Carolina, 25 degrees there in Charleston, South Carolina, and 27 degrees all the way down to the Jacksonville, Florida area. So this was a case of an Arctic outbreak of air. An Arctic air mass invaded the lower 48 during the winter time. All right, so classification of air masses. Air mass classification is based upon both temperature and humidity. So you need to think about both factors when we classify air masses. P, the capital P, stands for polar air mass. The capital T stands for tropical. A lowercase m, now that indicates an air mass is formed over a maritime area or a body of water. Lowercase c is a continental air mass. Okay, that means an air mass is formed over land. And then the last one there, the lowercase c, which means continental, and the uppercase A, Arctic, continental Arctic air, that is a special type of air mass that occurs primarily in the wintertime for the United States. Okay, so if we combine both the continental, the lowercase c, and the maritime, the lowercase m, we usually combine continental or maritime with either tropical, the capital T, or the polar, capital P. All right, so we combine letters like we're showing here with the continental Arctic air. And there'll be more to follow here as we move along in this lesson. Okay, so let's take a look at some of the air mass classifications and the characteristics. All right, the source regions are at the top of this little table. Arctic region, capital A is the abbreviation. Then another source region is the polar areas with a capital P. And then another source region would be the tropical areas. Typically, it's the tropical ocean areas, right? And that's abbreviated by capital T. Okay, and then you have source region as far as the land. So, for example, if I have an Arctic air mass forming over the land, that would be continental Arctic, or lowercase c, capital A would be the abbreviation. If I had an air mass forming over polar regions over land, it would be a lowercase c, capital P, or continental polar air mass. And then if I had an air mass forming over land, but also over hotter land, or tropical areas, that would be abbreviated as a lowercase c, capital T, continental tropical air mass. Right? So with continental air masses, here's some characteristics of those. They are usually extremely cold. If it's a continental Arctic air mass, it's extremely cold, it's dry, very stable. Continental Arctic air usually forms over ice and snow-covered surface areas. Okay? And you notice there's no formation of Arctic air masses over water. Okay? In the middle column there for continental polar air mass, it's usually cold, dry, and stable. If there is a polar air mass that forms over water, that would be known as an MP air mass, maritime polar air mass. And that is cool, moist, and unstable. A maritime polar air mass, cool, moist, and unstable. And then if I were to go over to the right there, continental tropical air mass is very hot, very dry, stable air aloft. It's unstable surface air. For continental tropical air, these are typically associated over the desert areas, especially over the southwestern United States. And continental tropical air masses only form during summer. Okay? And you may actually be driving on an interstate through the desert southwest, and you might see these dust devils kick up, those little whirly dust devils. And they typically form over a very extremely hot or heated surface over the desert areas. Maritime tropical air masses, those on the other hand are warm, moist, usually unstable. Now with maritime tropical air masses, this is the air mass that makes things very uncomfortable across the eastern United States during the summer months, especially latter July and August. Maritime tropical air masses typically move into the eastern United States, making for very high humidity and again, very uncomfortable temperatures overall. All right, so air masses of North America, and we'll move into the slide here in a minute. That's figure 8.2 from the 8th edition of the Essentials of Meteorology textbooks. We'll go into the air masses, and I'll show you what those look like graphically here in a minute. Continental polar air masses, CP, and continental Arctic air masses, CA, they originate over northern Canada and Alaska. They're both continental in nature, which means they both form over land, and they usually form at the higher latitudes, where you either have ice or snow, which that tends to, in fairly flat surface areas. Remember, we want something that's flat, and we want something of uniform composition. In this example, it would be the ice or snow cover. All right, and that cold air really gets going. You have a limited amount of daylight as well at the higher latitudes, so the air mass continues to grow stronger, much colder over time. All right, so air in contact with the surface, like I mentioned, with that ice or snow cover becomes quite cold and stable with continental polar and continental Arctic air masses. Now let me show you a graphic of a breakdown of all the air masses of the United States. Okay. The air masses that really impact the United States the most are the continental Arctic air, and you can kind of see at the very top of the image, CA is the abbreviation. That again is going to form well to the north over the frozen land masses of the northern latitudes in the northern hemisphere. Then you have continental polar air masses, which continental polar air masses can occur all year long, really. Continental polar air masses come down in the summertime into the northern plains, Midwest, as well as closer to the East Coast. And these give in the summertime, continental polar air gives a nice little break from the humidity, the high humidity. It kind of gives a little bit of a lower humidity feel to the air, which is a very nice break in all that hot and humid air of the summer. Maritime polar air masses, now those, maritime polar is going to form over water, over the North Atlantic and the North Pacific Ocean, and it's going to mainly impact the northeastern United States, the New England area, down to the mid-Atlantic, maritime polar. And then it also impacts the west coast of the United States, maritime polar. And then we have maritime tropical air masses, which form over the very warm waters of the tropical regions. And as I mentioned, maritime tropical air masses are very muggy, especially in the eastern United States during the summer months. Makes things feel very uncomfortable with high humidity. It also forms over the Gulf of Mexico, so many of you, if you are in the Pensacola area, you're very familiar with how muggy and just hot it feels during the summer months, and that's due to the maritime tropical air mass, the MT. And then, again, as I mentioned, summer-only type air mass is the continental tropical air mass, which forms over the desert southwestern United States. All right, so now moving on to just another example of air masses. Air masses, basically, they're separated by what's known as fronts. And we'll get into the types of fronts here after we talk about air masses. But in this example, this drawing, you can see there's a orangish red arrow with a 55 degree temperature, 55 degrees Fahrenheit, out ahead of a approaching cold front. There's an Arctic air behind the cold front, and you can see how big of a temperature difference there is from 55 degrees Fahrenheit all the way down to minus 20 degrees Fahrenheit, below zero temperatures. So this is an example of very strong cold front, very strong Arctic air that's pushing southeast towards the Midwestern U.S. in this example. All right, we're going to also take a look at another example here, just showing you some of the colder outbreaks that we've seen. Now, I'm not showing you the Siberian Express of 1983. In December of 83, there was extremely cold temperatures that came down. Continental Arctic air came into the United States during the December 1983 time period. Go ahead and look it up if you're really curious, but it broke some of the all-time records in the United States. They called it the Siberian Express of December 1983. I believe it's mentioned in your textbook as well. Here's a couple more examples besides that Siberian Express, the Arctic outbreak of 83. 1989, there was a really cold shot of continental Arctic air that came down into the eastern United States. This is showing you some of the temperatures associated with that outbreak of cold air. Negative 30 degrees up in North Dakota, Bismarck. Also negative 20 at St. Louis, negative 12 Chicago, negative 12 at Louisville, and all the way down to 9 degrees above zero at Washington, D.C. in 1989. And even in Florida, 9 degrees above zero in Pensacola in 1989 in December with this outbreak of Arctic air. So it definitely was a much colder feel right before the Christmas time period that year. And there's another outbreak that came down in 1990, a little bit further west, as indicated by the blue arrow. And that also occurred in December, where you had negative 38 in northern Montana, negative 29 degrees Fahrenheit in Boise, Idaho, negative 28 down into Utah, and all the way down to negative 6 down in New Mexico. So again, these continental Arctic air masses typically occur in the winter. The sun angle is much lower, the solar radiation is much weaker, and then you get the jet stream to basically the polar jet stream comes down straight from the Arctic and continental polar source regions to really give us a cold feel to the air down here in the United States. Okay, here's an example. We're moving on now to what it looks like when cold, dry continental polar air masses basically move off the United States over warmer waters of either the Western Atlantic or the Gulf of Mexico. You notice what happens? You get this cold, dry continental polar air, and once it goes over that relatively warmer water, it tends to form clouds, and there's a distinct edge to those clouds. If you look off the east coast of the United States in this image, you definitely can see there's, by the direction of the purple arrows, the general wind flow as that cold, dry continental polar air mass comes off of the United States over the relatively warmer waters of both the Atlantic and the Gulf of Mexico. This forms what's typically known as cloud streets, and you'll just see all these clouds, and you may have some showery precipitation out over the water when you get this to occur. All right, so now we're going to continue our talk. We already talked about continental polar, we talked about continental Arctic air, CP and CA air masses. Now we're going to move into a discussion on maritime polar air masses, MP, And maritime polar is a cool, moist, and unstable air mass. The source regions for maritime polar air masses originate over Asia and the frozen polar regions. Okay, I want you to think about maritime polar air masses in two main locations that impact the United States. One is over the North Atlantic Ocean, and the other is over the North Pacific Ocean. For maritime tropical air masses, empty air masses, these are typically warm and moist air masses, and they typically occur or form, the source regions are subtropical, central, and eastern Pacific Ocean, as well as the Atlantic Ocean, okay? Gulf of Mexico, think those locations for source regions for maritime tropical air masses. Okay, so what happens when some of these air masses, what happens when they come into the United States? All right, this is an example on this image of a maritime polar air mass, MP air mass, and it's making more of a cyclonic turn. So a cyclonic, as indicated by that blue arrow. So typically in California, for example, in the wintertime, the maritime polar air mass can really result in very cool and showery type weather. There can even be, if there's enough energy in the upper levels of the atmosphere, there can even be thunderstorms down into Southern California when you have these stronger maritime polar air masses that move cyclonically, rotate cyclonically into California. All right, and what happens here in this image I'm showing you is maritime polar air masses moving into the United States a little bit further north into the Cascades, the Olympic Mountains and Cascade Mountains of the Pacific Northwest. Keep in mind, maritime polar air masses are a very commonplace from Washington State, for example, Seattle, all the way down to Portland, Oregon, all the way down through California. So when maritime polar air comes in, I'm showing in this diagram, it's a cool, moist air mass initially. And as that maritime polar air mass moves in and collides with the Olympic Mountains and the Cascade Mountains, what happens is on the windward side of the mountains, you get all the precipitation and the moisture. In this case, I'm showing heavy rain. On the leeward side, okay, the air sinks as indicated by these purple arrows. And as the air sinks down the leeward side of these ranges, these mountain ranges, it's a much different climate. Very dry, in fact. As the maritime polar air mass gets modified and moves further inland towards the Rocky Mountain states, into the Rocky Mountains, the air once again rises up the windward side of the mountain slope, and then it once again will sink down the leeward side. And when we're mild in the United States in the wintertime, typically what happens is you get more of a west to east polar jet stream, and all the moisture is basically precipitated out of the clouds on the windward side of all these mountain ranges. And on the leeward side, the air mass is modified. Once that moisture is removed on the windward side, and as the air sinks on that leeward side, it's going to dry out and become more mild. So typically, that's what happens in the United States during a warmer or milder pattern. When you're talking about December and January particularly, you get a east to west or west to east jet stream, and you get these maritime polar air masses pretty much moving across the country. Here's another great image showing you maritime polar air masses moving into the United States. This is an example not only of maritime polar. If you look at that yellowish orange big arrow there, okay, this is something known as a pineapple express, okay? And why do we call it pineapple express? It's because all this moisture in association with the maritime tropical air mass, all this moisture and a stronger subtropical jet stream, it's all pointing towards California and the West Coast as a whole. So we call it pineapple because the source region is generally from around the Hawaiian Islands. So it's called the Pineapple Express. A lot of moisture. This can result in flooding, especially into California. It's very commonplace. But just this is what happens when you have a maritime polar air mass colliding with a maritime tropical air mass in the Pacific Ocean. And then you get an energized jet stream there, as indicated by this yellowish orange arrow, and all that moisture is directed from the southwest to the northeast towards the west coast of the United States. So you may hear meteorologists in the wintertime on TV say, "Oh, looks like a pineapple express," or you might look at the National Weather Service out into California. They might refer to this in their forecast for discussions as well, the Pineapple Express. All right, now we're moving on to continue our discussion. We're about wrapped up on air masses, but we need to talk about the continental tropical air mass now. This is abbreviated with the letters CT. And a continental tropical air mass is that hot, dry, is conditionally unstable in the lower levels close to the ground where that air is so intensely heated. And like I mentioned earlier in this presentation, there's frequent dust devils associated in the desert areas with CT air masses during the daytime when the heating is at its greatest and the sun is at its highest point. And continental tropical air masses are found during the summer, typically in northern Mexico and then also into the southwestern United States. Okay? And remember that CT air mass only forms in the summertime. Right, so here are some of the temperatures associated with a continental tropical air mass, and it gets hot from Las Vegas into Southern California, Palm Springs, into Death Valley in California, also into parts of Arizona, New Mexico. This is where the air mass really, really heats up. And if you remember from earlier on in the course, I mentioned that dry air has a tendency to heat up and cool time 5 times faster than moist air. So we're talking about extremely dry, arid areas of the United States in the summertime that get very little rainfall. And so the sun is, again, at its highest point throughout the year. The radiation from the sun is very intense. The heating is more direct. And this results in conditionally unstable air at the surface. And what happens over time is you get these whirling dust devils that kind of spring up from the surface, working their way upward in the atmosphere to try to redistribute that heat energy aloft, higher up in the atmosphere. So it can be very hot. If you see a weather map in the summertime over the desert southwest, like I said, Nevada, Southern California, Arizona, and New Mexico, triple-digit heat. It's typically associated with continental tropical air masses. So now that we're done with our discussion on air masses, let's move into the discussion on what separates air masses, and that would be fronts. Okay? A front is a transition zone between two air masses of different densities. Now, there are many different types of fronts, and we're going to kind of talk about the characteristics of each as we move forward now. We're going to start with the stationary front. And the stationary front is exactly what stationary means. It just doesn't move a whole lot. Essentially, there's no movement with a stationary front. The winds tend to blow in parallel but opposite directions on either side of that stationary front. There's really nothing pushing the front along to actually cause it to move. The winds are opposite and opposing each other on both sides of the front. Right? Here in this example, I'm showing you what a cold front would look like. Okay? And if we were to look at the atmosphere from a side shot, there you can see that sloping nature to that blue color there. It almost looks like a ramp. That is an example of a cold front. Now, there's two types here I'm showing you in this graphic. One is a polar front with warm air out ahead of it, and the other is an Arctic cold front, which has extremely cold air behind it. You get those Arctic frontal passages typically in December and January, even into February, as the northern air mass source regions are extremely, extremely cold with very little sunlight. I want you to realize one other thing before I move on. A cold front typically has a much steeper slope, which means let's say, for example, 1 mile in the horizontal, maybe 50 miles in the vertical for the slope of a cold front. So it's very steep. All right, also I just wanted to show you this map, looking at the United States as a whole. This looks like it's a map in the wintertime. We have a lot of variety of different colors on this map. Right? We have a lot of different weather fronts on this map. The purple line, so you see that red L there over the northern lower peninsula of Michigan. Okay, there's a purple line that kind of extends out of that red L, and that is known as an occluded front. It's purple, it has a triangle and a semicircle on the same side. You can see the simplified key there on the bottom right of this image too to kind of help you identify the different types of fronts. But the occluded front is identified by a purple colored line, and it has both the triangles and the semicircles on the same side of the line. The red line with the semicircles kind of on the above the red line, that is known as a warm front, that red line. And then the blue line with the triangles, those blue triangles kind of pointed downward, that is a cold front. Okay, and then further west, out towards Montana, Wyoming, Colorado, there's alternating red semicircles and blue triangles. That is a stationary front, which just really isn't moving a whole lot. In this case, we have maritime tropical air mass coming in out of the Gulf of Mexico on the backside of high pressure, which is situated over the Florida Peninsula. So you have maritime tropical air or empty air coming up, southwesterly winds out ahead of the cold front. And then you got a switch in wind direction to the north and northwest behind the cold front. So temperatures are much colder. For example, in this particular image, Chicago is 25 degrees at this point in time with light snow. St. Louis is 23 degrees with strong northwesterly winds at 25 miles per hour. Out ahead of it, you still have some colder air over Pennsylvania before the warm front moves through. You got 28 degrees in Pittsburgh, in that Pittsburgh area with light snow. A mix of rain and snow in Washington, D.C. at 31 degrees. Further south, you get a little bit warmer into North Carolina with that light southeast wind, 34 degrees with some light rain. This just gives you a great example of how busy a weather map can actually be in the winter months across the United States. All right, so cold fronts, we talked about a stationary front, just really doesn't move a whole lot. Cold fronts, on the other hand, are cold, dry, they have stable polar air behind them. That replaces that warm, moist, unstable air, this tropical air out ahead of them. There is a special type of cold front that's known as a backdoor cold front that actually comes down from the northeast and actually moves south-southwest. Normally cold fronts in the United States will move from northwest to southeast, but in the case of a backdoor cold fronts are typically associated with maritime polar air masses, and the cold front will actually come from New England and go down the east coast of the United States from a north-northeast to a south-southwest direction. So those are kind of unique backdoor cold fronts. All right. Here's an example of a cold front, again represented by a blue line on a surface weather map and the blue triangles. Warmest air is out ahead of the cold front, and then the coldest air by the blue arrow there, represented by that blue arrow, that's colder air coming in to replace the warmer air out ahead of it. Typically you will get showers along the cold front as well, as indicated by the green color, or some sort of precipitation. Anytime you have a frontal system moving in with differing air masses, different density of air masses, you typically get air that rises in the atmosphere, produces clouds, and some sort of precipitation with frontal boundaries. Here's an example of what a area of precipitation looks like in association with a surface cold front on a weather map. You can see a lot of green in this image. You also see a lot of yellow, higher reflectivity yellows and oranges out ahead of the cold front. And that is typically associated with scattered thunderstorms. One thing I will mention in the warmer months, well, really mainly in the spring, late spring, early spring to late spring time period actually, you can get what's known as squall lines, which are lines of intense thunderstorms that typically form out ahead of a cold front. So squall lines are associated with cold fronts. Here is an example of a cold front looking at everything from the side, kind of like a three-dimensional view. The warm air is represented there by the orangish arrows, and the cold air is represented by the blue arrow. Now, colder air is much denser or heavier than that warmer air. The warmer air wants to rise, it wants to seek out where it wants to be. And that warmer air is so less dense and so less buoyant that it wants to rise out ahead of the cold front. As that cold air comes in at the ground, it's basically lifting all that warm air off the ground. And if the air is unstable enough, get a lot of warmth and moisture out ahead of a cold front, you can get severe thunderstorms, you can get tornadoes, you can get cumulonimbus clouds, which is our thunderstorm cloud we learned earlier on in the course. So weather can be quite active in association with cold frontal passages. And again, remember that the slope associated with cold fronts is much steeper than any other weather fronts. Okay. Here is an example of a backdoor cold front. Okay. So typically you get maritime polar air that is moving clockwise around some sort of high pressure system. Typically the high pressure system is over southeastern Canada or into the New England states, especially like Maine, and you get a clockwise flow around that high pressure system. That's maritime polar air coming in off the unfrozen waters of the North Atlantic Ocean, and it generally pushes from the north-northeast to the south-southwest, which is not typical in the Northern Hemisphere or in the United States as a whole. So this can result in a nice little cool down. Usually brings in some low clouds, some stratocumulus clouds off the ocean area. Whenever this air mass comes in, winds usually shift more of a northeasterly direction with maritime polar air masses. Here is the typical weather conditions associated with a cold front in winter in the Northern Hemisphere. This is a really great table. I'm not sure what table it's in the 7th edition textbook, but the 8th edition textbook, it's table 8.2. Now this is really good to know. Okay, the weather elements we're looking at are winds, temperature, pressure, clouds, precipitation, visibility, and dew point. Okay, so before passage of a cold front in the Northern Hemisphere, the winds are generally out of the south or southwest. Okay, we usually have warm temperatures out ahead of the cold front. The barometric pressure falls, it drops steadily. And then clouds, you typically see increasing cirrus is the first indicator of a front moving into the area. Those cirrus eventually lower to cirrostratus clouds, which we talked about earlier in the lesson, in the course. Cirrostratus clouds are typically associated with halos around the sun or moon. And then that cirrostratus layer will lower. If the air mass is unstable enough, it will become towering cumulus or cumulonimbus, but it has to be unstable air mass. Okay. Precipitation out ahead before passing through the area for a cold front usually get showery precipitation. And what I mean by showery is the precipitation starts and stops really quickly. You may be looking out your window and you see all of a sudden there's a downpour, and then you look out the next minute and there's nothing going on. The precipitation completely stopped on short notice. So you get more of a showery nature to the precipitation out ahead of a cold front. And the visibility is usually fair to poor. It can be poor in haze and also in heavy downpours that kind of start and stop quickly. The dew point will remain high before a cold front passes. Okay. Now, when the cold front actually is starting to move through the area, while passing, your winds are going to become more gusty. They'll start shifting direction. The temperature you'll start feeling a sudden drop in the temperature. The barometric pressure will be at its lowest point when that front is basically passing through. As soon as that front passes through, that barometric pressure is going to be on a sharp rise. It's going to want to increase. Clouds right along the frontal passage would be towering cumulus or cumulonimbus once again for an unstable atmosphere. Now, if the air mass is stable, you may have more of a nimbostratus, a rain-producing layer-like cloud. Precipitation while passing through will be heavy showers of rain or snow. It's wintertime, you get heavy bouts of snow, very showery, starts and stops on short notice again. Sometimes you get hail if the atmosphere is unstable enough, thunder and lightning with those thunderstorms as it passes through. And then as the cold front moves through, it passes, the visibility will be poor in the heavier precipitation, but then it will be followed by an improvement in your visibility. And then dew point will be a sharp drop in that. It's going to fall rather quickly once that front moves through. Now, after passing through, what's going to happen to your winds behind a cold front? Your winds are going to shift to the west or northwest. This is going to blow in much drier air masses. Temperature is going to drop. Your barometric pressure will rise steadily. The clouds are often cumulus right behind the cold front in the more unstable air masses, maybe stratocumulus when ground is warm. Okay. And then precipitation after cold frontal passage will decrease in intensity, then there'll be complete clearing. Visibility will be good except in the showery precip, and then the dew point is going to drop fairly significantly, depending on the strength of the cold front and the time of the year. Now, next moving on to warm fronts. Warm fronts contain warm, moist subtropical air from the Gulf of Mexico, and those are typically associated with maritime tropical air masses, replacing cold maritime polar air. Overrunning occurs. Sometimes you get maritime tropical air masses that replace continental polar air masses, in the wintertime, especially along the Gulf Coast as well. I've was down in the Pensacola area myself for about 2 years, and whenever you get that warm, moist, maritime tropical air, that southerly wind to blow in from the Gulf of Mexico in the wintertime, over a retreating continental polar air mass. So you may have had high pressure, clear skies for 1 to 2 days. Continental polar air mass is in control. Once the high pressure shifts off the coast, the winds move more from the south. They blow more from the south over the warmer waters of the Gulf of Mexico, and you get maritime tropical air mass that starts overrunning that cooler surface, or the cooler air that was in place, the cooler ground, and you can get some really dense fogs. I've seen some really dense fogs in the Florida Panhandle, especially during wintertime when this type of stuff happens. So you get overrunning of moisture, you get rising of warm air over cold. Another interesting feature is what's known as dry lines. Now this is more so along out towards Texas. Dry lines are more towards Texas and the Oklahoma area, the Texas Panhandle and Oklahoma. Basically, a dry line is a moisture front or a dew point front. There's dry air along the boundary. The dew point temperatures may drop along this boundary by as much as 18 degrees Fahrenheit in 1 kilometer. So 1 kilometer is about 0.62, just over half a mile. So you can have an 18-degree temperature drop in just half a mile distance with a dry line passage. Okay, dry lines are very interesting because there's not really much of a temperature difference ahead and behind them. It's more of a moisture difference. And keep in mind that moist air is much less dense than dry air. Dry air is heavier than moist air, so usually you get a lot of moist air out ahead of the dry line. Air wants to rise, and then you get the drier air behind the dry line passage over Oklahoma into the Texas Panhandle. Some of the largest hail and severe weather is associated with dry lines, believe it or not, out into Texas. Okay, moving on now to an example. Here showing you the different wind directions associated with fronts. This is with a warm front. So with a warm front, you typically, the sequence of winds out ahead of a warm front, okay, the air is generally pretty cold, and you usually have more of a northeast or maybe an east-northeast wind. Over time, as that warm front approaches the area, those winds become more southeasterly, and then that's when you really start getting some warmer air to move in ahead of the warm front, where the winds go southeasterly. Once the warm front moves through the area, your winds will shift to the southwest. So if you see a southeasterly wind, it's still kind of chilly, but you kind of feel like the air is getting milder, and then when that warm front moves through, the maritime tropical air mass moves through, then the wind usually shifts to the southwest at that point, after warm frontal passage. Okay, and here's an example from more like a side view, a three-dimensional view of a warm front. Generally, you have, with warm air, it tends to be, with a warm front in general, it has a much shallower slope than a cold front. So it's greater distance in the horizontal than the vertical. It spreads out over a larger area in the horizontal, the air mass. So if you look at this particular image, you'll see that the warmer air is less dense than the colder air. So the colder air is going to remain near the ground, being denser. The warmer air is going to basically ride up and over. It's going to glide up and over the colder air at the surface. And as a result, when anytime you have air rising, it's going to cool and condense and form clouds and some sort of precipitation. So with cold fronts, we have more showery precipitation. I mentioned that. With warm fronts, we have more steady or continuous precipitation, and it usually tends to be lighter with warm fronts. Okay? In this example here, I'm showing an image of the different cloud types associated with as you get closer to that warm front. You may initially see just the high, wispy cirrus clouds lowering to cirrostratus, where you see the halo with cirrostratus around the sun or moon. Those cirrostratus may eventually lower to the mid-level altostratus clouds, lowering even further to the nimbostratus and even the stratus. Especially in the wintertime, you can get stratus, which forms fog closer to the ground in association with warm frontal passages as that warmer air moves in to the cooler air mass. This is an example of a dry line. This was the dry line, the special type of boundary. Air out ahead of the dry line is way more moist. Like I mentioned with the dry line, though, look at your temperatures. The temperatures are the the number there attached with each station plot here. The air temperatures are the upper left-hand number. Okay. Notice the temperatures in the upper 80s out ahead of the dry line, and they are slightly warmer behind the dry line. They're actually into the 90s. Okay. One main thing I want you to notice though is the bottom left-hand number in this image. Out ahead of the dry line, look at your dew point temperatures. The bottom left number in each station plot is the dew point. So look at your dew point temperatures there in eastern Texas. 68 degrees Fahrenheit, 66. I see a 70 degrees Fahrenheit, a 72. Then after the dry line passes, your dew points are down to 36 degrees Fahrenheit. I see a 32, a 34, a 31, another 36. That is a really abrupt change in the moisture over a short distance. And that sometimes is enough to really spark some severe thunderstorms, especially over northern Texas into Oklahoma. You can get some really large hail. Some of the most damaging hail on record has been in association with the dry line down into Texas. And behind that dry line, you typically get a hot, dry, continental tropical, or CT air mass. Ahead of the dry line, you have more of a warm, moist, maritime tropical, or MT air mass. All right, so here are the typical weather conditions associated with a warm front in the northern hemisphere. So notice, we're talking about the same elements we did with the cold front table. Winds, temperature, pressure, clouds, precipitation, visibility, and dew point. So before passing, the winds in the northern hemisphere with a warm front are typically out of the south or southeast. While passing through, those winds become variable, and then after the warm front passes, the winds become more south. More typically, they become southwest after warm frontal passage. The temperature before passing is generally cool to cold, with a very slight warming trend to those temperatures before the warm front moves through. While passing through, there's a steady rise in temperature, and then after warm front passage, it's warmer temperatures, then overall steady. The barometric pressure before passing is usually falling or dropping. While passing, the pressure levels off. And then after passing, after that warm front moves through your area, you'll see a slight rise in the barometric pressure followed by a fall. Okay, you'll see that slight rise as the warm front moves away, but then it starts falling again, the pressure, because usually you have a cold front that's eventually going to come in from the west, and that's going to cause that pressure to drop again. With clouds, before passing, there's a definite sequence of clouds in association with warm fronts, starting with cirrus, cirrostratus, altostratus, nimbostratus, stratus, and fog. Occasionally, if the air mass is unstable enough, you get you get the cumulonimbus cloud or thunderstorm cloud in the summer. While passing through with warm fronts, you typically get more of a stratus type cloud, and then behind the warm front, you get clearing with scattered stratocumulus clouds, especially in summer. Occasionally, cumulonimbus, the CB clouds in summer. If the air mass is unstable, you get those thunderstorms. Precipitation is more continuous with warm fronts. Light to moderate rain, snow, sleet, or drizzle. You may get more showery precip in the summertime just due to the nature of how hot the ground is heated. While passing through warm fronts, have drizzle or no precipitation, and then after passage, there's usually none. No precipitation. Visibility with warm fronts before passing, usually very poor. While passing through, poor, but then it steadily improves. And then after passing with warm fronts, the visibility becomes fair. You sometimes get haze. And then the dew point, which is the amount of moisture you have in the atmosphere. Before warm frontal passage, it's a steady rise. While passing, the temperatures remain fairly steady. And then after passing through after the warm front passes through the area, you'll get a rise in the dew point and then steady. Okay. All right, next we're going to talk about occluded fronts. Occluded fronts are interesting because they're a combination of both cold and warm fronts. So what happens is you have a frontal boundary that's created between two air masses, and with an occluded front, it occurs when a cold front catches up to and overtakes a warm front. Okay, and this happens because the colder, denser air is that cold, dense air is way more fast. It moves much quicker than the warmer air out ahead of the cold front. So eventually what happens is that forward momentum, that forward speed catches up to the warm air and lifts that warm air completely off the ground in the case of an occluded front. So you have two types of occlusions. I'm showing you one of them here is a cold occlusion, with air behind the occluded front being the coldest as compared to air out ahead of it. There's also a warm occlusion as well. Now looking at fronts from the side view, this is just showing you what an occlusion looks like. I have some letters here, A, B, C, and D. These are my images. With a cold type of occlusion, you typically have the very cold air, the coldest air, back behind the occluded front. Just showing you, generally, you get precipitation. That's kind of a mixture of both a cold and a warm front with an occluded front. Here is an example of typical winter weather during the winter time, most often associated with occluded fronts in North America. Generally, it depends on if it's a cold type occluded front or a warm type occluded front. But with any frontal system as it moves into the area, it's gonna result in falling barometric pressure out ahead of it, and the air pressure will usually rise behind it. And the precipitation really depends on whether you have a cold or warm type occlusions. Cold type occlusions you get more typical cold frontal weather, more showery precipitation. With warm type occlusions, you typically get more of a warm frontal type weather. Okay, and then I won't read everything off this one. I'll give you a minute here to kind of take a look at this. It's also in Table 8.4 in the 8th edition Essentials of Meteorology textbook, if you want to examine this even closer. Here is an example of a cold occlusion in the wintertime. Cold occlusions typically happen over off the east coast of the United States during winter, when you have much colder continental polar air behind the occluded front pushing off over the relatively warmer waters of the western Atlantic. So you typically have much colder air behind the cold type occlusion than you do out ahead of it. All right, now we move into the final topic of the lesson, and we're going to take the next 14 slides here, the last remaining 14 slides, to really talk about a topic I really, really enjoy. This is mid-latitude cyclonic storms. Okay, these particular systems, all this material I'm going to go over will help explain why storms get stronger, what are some of the dynamics, even the upper levels of the atmosphere that kind of help feed or strengthen surface low pressure systems. So the first thing we want to talk about is the polar front theory. A polar front is a semi-continuous global boundary separating cold polar air from warm subtropical air. That's exactly what the polar front is. These wave cyclones tend to form and move along the polar front in a wave-like manner. So they're known as wave cyclones because they form in a wave-like manner along the polar front. So I want you to think about that polar front being a semi-continuous boundary that separates warm subtropical air from the mid-latitudes. It separates that air mass from colder polar air from the higher latitudes. These frontal waves form under the right conditions in a wave-like kink. All right, you see like a little bending or a kink in those isobars. Okay. Let me show you an image of what happens here with the polar front theory. Okay. By the way, this was developed back in World War I by the Norwegian School of Meteorology, and during World War I, we talked a lot about, there was a big talk about battlefronts, and the whole concept of battlefronts, the analogy kind of tied in with battlefronts associated with mid-latitude cyclones and the polar front in general, that it's a battle zone, just like World War I, when armies clashed, there was a battle zone of fronts. Same thing happening here with cyclonic storms, okay? So in A, you start off with a stationary front, and with a stationary front, as I mentioned earlier, you typically have two opposing air masses that kind of just blow parallel to each other. They don't really mix with each other. So you have colder air to the north of the stationary front, and then you have warmer air to the south of the stationary front. As we move to B, letter B there, that middle diagram there, the upper row, we start getting an area of low pressure to form along this polar front, okay? And the colder air starts to basically turn and mix with the warmer air, while the warmer air moves towards the colder air and starts mixing, tries to rise and mix with that. In point C, or diagram C, I'm showing a much more developed area of low pressure along the polar front, okay? And now we really got the air masses mixing. The storm is intensifying or getting stronger. By point D, we reach an occlusion, an initial occlusion state. We get that occluded front to initially form during the mature stage of a wave cyclone. In that image there, the bottom left, and you get a lot of heavy precipitation. This is when the storm is at its intensity, its peak intensity during the mature initial occlusion stage. And then as air masses continually mix with each other, eventually the air mass contrast will dissipate, so there's not as much of a strong air mass temperature difference across the frontal boundaries, and that's known as an advanced occlusion. This is the decaying stage or the dissipating stage of the wave cyclone. And then in letter F there, the bottom right-hand image just shows how the polar front kind of just reforms back into a stationary front, waiting for another bit of energy to move over it to develop another area of lower pressure. The initial parent low pressure system that was attached to the fronts has now drifted off to the colder air to the north. Okay. Here's an example of mid-latitude cyclonic storms, generally along the polar front. And typically the polar front is around 60 degrees north latitude in the northern hemisphere, where you have the cold polar air meeting the milder mid-latitude subtropical air. But in the wintertime, because of the polar jet stream dipping much further south, the polar front can actually extend into the United States. Okay, so this is just showing you how continuous this frontal system is, the frontal boundary is, the polar front. Areas of low pressure in this image over near Alaska. We've got our frontal and occluded front extending southward, and then eventually extending southwestward into the northeast United States with another area of low pressure, and then that extends further back towards the Rocky Mountain states. So you can see there's just these little waves, these little red L's, little waves of low pressure that form along this front. Okay. All right, so moving on. Where do mid-latitude cyclones tend to form? They generally tend to form along lee sides of mountain ranges. They're also known as nor'easters in the east coast in the wintertime, the Hatteras Low, Alberta Clipper, and Colorado Low. Okay. This is an example of air flowing down. Okay, I've got about 13 minutes remaining. I'm about to run out of battery life here. Apologize for that. But this shows you in the lee side of mountains, areas of low pressure can form. Mid-latitude cyclones, these are the different tracks that typically occur. There's a Colorado low track, there's the Alberta Clipper, the Gulf of Alaska low, the Hatteras low, and the Gulf low. Right? And mid-latitude cyclonic storms, they generally rely on either divergence or convergence aloft. Okay? With mid-latitude cyclones, we want upper-level divergence or spreading of air aloft over the surface low. With anticyclones or high-pressure systems, we want areas of upper-level convergence, which results in sinking air motion. Okay? Here's an example, mid-latitude cyclonic storms. I'm not really going to hit on that too heavily. This shows you over surface low-pressure systems that you typically have areas of upper-level divergence aloft, higher up above surface low-pressure systems, which results in rising air. And then you have upper-level convergence, or the air coming together aloft, higher up, in sinking air associated with surface high-pressure systems. That's very important. The upper-level support is very important in developing these systems. Okay, all right. So you get these waves in the westerlies. Wavelength, you get these long waves and short waves. Long waves are typically at 300 millibars or 30,000 feet. And then short waves are typically about 18,000 feet, even down to 10,000 feet. These waves in the westerlies and the upper levels are your upper air support for developing storms. Okay. And then moving on. The role of the jet stream, I just want to hit on that, and then we'll be wrapping this lesson up. The polar jet stream removes air above the surface, low pressure system or cyclonic storm, and supplies air to a surface anticyclone or high pressure. The upper air support, when you look at the atmosphere, you got to look at 3 dimensions. It's not just a 2-dimensional thing. It's all, you got to look at all levels of the atmosphere from the surface all the way aloft. Here is an example of the polar jet stream in the upper level chart situated above the surface low pressure and high pressure systems. Remember this, divergence, if you have more divergence aloft, then you have low level convergence, then the storm will intensify. Divergence is necessary for the rising air motion, the clouds and precipitation associated with surface low pressure systems. And then convergence, upper level convergence, results in the piling up of air aloft and sinking air motion associated with high pressure systems. All right, that wraps things up. We talked today in the lesson about air masses, the different types, frontal systems, cold, warm, and occluded, and we even threw in a stationary front there, talk about that. Mid-latitude cyclones as well. Okay, I appreciate your attention in the lesson, and I hope everybody is having a great day. Best wishes to everybody, and continue to study hard.